מאותה. גיל מה? איזה מילים.
מה, שחסר באיזה?
חוצפה למה, רודנס.
לא, כולם אומרים באיזה, כולם אומרים חוצפה באיזה.
חוצפה זה רק, אני לא אמרתי בחיים חוצפה.
לא, זה גם בחלק מהעברית. אומרים זה במבטא, אמריקאים, כי אומרים את זה, כי אין להם את המילה נתח על כך דבר.
אבל זה מספיק שזה, זה לא...
באיזה הקשר זה נאמר?
חוצפה זה לא... מתוך המילים העבריות לא
נו, אבל יש את זה.
אין את כל זה, שלושת הגינה.
לא, אבל יש...
לא. אבל יש כזה כמילה לקלל.
טוב, זה קטע... זה אפילו לא קטע עברית. כאילו...
אין את כל המילים שהגיעו מהארמית.
מילים מהארמית. חדשתי שיגיע הארמית.
נפקא מינה. איך תגיד נפקא מינה באנגלית?
practical application. הגיע לי איזה ביג פאנול.
קישריה. יותר אבל נגיד קישריה?
כן, קישריה. זה מהפסיכומטרי.
זה מה?
מהפסיכומטרי.
כולנו אני רוצה גם לדבר כשאומרים משהו הוא מהפסיכומטרי.
זה לא בעברית. זה מה זה קישריה?
אי אפשר להגיד קישריה. זאת אומרת מטבע בתוך פחית, כאילו, זה אחד, פחית עושה הרבה רעש. הוא יכול, זה בדיוק לבן אדם שיש לו... שיש לו דבר מעט מאוד והוא מתגאה בזה ועושה...
קשקש מה? איסטרה בלגיניה? בלגיניה. בסדר, אני לא קוראת את זה. אני יודעת לכתוב את זה. בלגיניה זה כמו... בלגן. מטבע.
או איסר.
מעצר.
זה לא באמת מה שתשמע אנשים אומרים, מה תדאג?
איסר זה מטבע.
זה... אפשר משהו לשפה עתיקה שהיא מחלטים.
מה אתה נושא או מנסה?
להגיד להם את זה.
עוד גיל.
No, it's not. Aramaic is not old English. It's a language that's spoken around Iraq, right?
שפה שמית, לא?
It's a Semitic language, like Arabic, but in Hebrew there are many different languages, and also the Haggadah,
No, very small portion of Haggadah.
לא יודעת, יצא לי אנגלית. אז חגיה, זה בערבית.
כן.
לא, אבל טוב, אמרת לך שירים שם בטוח. באמת? זה כאילו השירים שם.
גם כשלא מגיעים קופצים אליו.
בדיוק, זה החלק
זה לא,
שווה.
זה אחד מיודעתי.
אז באיזה שעה כאילו מרשים?
שולחן ערוך
שולחן ערוך, איזה אנשים מתנהלים. עשו את שולחן ערוך, מעיינים בהלכות, ראשונים, אחרונים. מה אמרו לתוספות?
קרה שהרגיש. לי אחת הבדיחות קרובות שלי בשולחן, כל פסח מחדש.
הרבה מילים גם בעברית התבססו על שורשים לאנגלית. מסוק.
נישואים,
אז זהו, שעברית נסק.
זה השור שלו על זה.
נון במקום
ואז כאילו, כשאומרים דברים שעולים, קומפסיק, זהו, מסוק.
זה הנון, זה בא או כל מה שנגמר באלף, כמו דוגמה.
מערבית כמו מעשים לעלות. ליטרלי המשמעות. המשמעות של העברית. ויש כמו עלייה. כמו שנגמר באלף, כמו אבא. אמא. בעברית כתוב אב ואם.
לא כל, אבל הרבה.
סבא.
בגמרא, כן, גם גמרא זה באלף.
אבא, מינה, אמינה.
פורסה. פורסה.
סופה for one.
כן. American Concord.
אלמלא. בשניהם.
מחפשים מילים בערבית שלי.
לא, יש את זה בערבית.
כן, אמרנו את זה כבר.
וואלה.
בגין נותן פה מילים שאתה לא
כאילו,
חושב.
למקט אתם כמו שהיה בסביבות, יש דילמה.
זה מארמית.
שם, יותר מהשם.
שם.
Good afternoon. While I'm setting up, I was approached last week about the date of the exam. So currently the exam is set up to be in the first week after the end of the semester. I think on Thursday. And I understand that people here feel that this might not give you enough time to prepare. Now the reason we chose this date is that I will be away afterwards until the end of the semester break. So, but I think that we can nevertheless postpone it. So, but it depends on agreement, of course. The drawback is that I will not be here physically, but no, it's not question. Why is this so funny?
Spiritually.
What? No, I will explain. Spiritually, I will be here. No, but more than that, I can be, online, so that if Neta feels that there's a question that she needs to consult with me, she can talk with me, and that's what that's what I meant. And we can solve the technicalities involved in grading the exam. So I don't remember the exact date that we were thinking of. It's the 15th. So I just want to point this out to everyone. I don't want to have now a discussion on this, but the regulations are that to change the date of an exam, there's a need of agreement of everyone. So if anyone objects, come to talk with me or with Neely.
What is the new date?
I think it's the 15th. But we chose it. I don't think that there was a very strict reason to choose specifically this date. So for someone here it's problematic. You might be able to look for another date. Yeah, let's discuss this afterwards. I think there's also there's also plenty of time, so that's why I don't want to discuss it now. Okay. Microphone. Okay, so we discussed last week gradient descent in the context of feed-forward network, so it was more than just discussing gradient descent. We discussed the backpropagation algorithm, but now I want to discuss a different type of learning scheme, which is quite general. Can be applied also of course, to neural networks. We can imagine perhaps that this kind of learning might happen in the brain, but for now we discuss it as a general form of learning, and it's applicable in many cases in which you don't really know how to calculate the gradient of the error for all for general example for all the examples. Actually, for now, we will start by assuming that we do know to calculate the gradient, but okay, maybe I will explain the context and then you will see why it's useful. So the topic is stochastic gradient descent. And let's start by reviewing what we've done typically so far. So far we imagined that we have a set of examples, the training examples. Maybe they were drawn from some distribution, but they're given. And our goal is to, what we try to do is to minimize the training error over these examples, with the hope that this will also give us a low generalization error. So training error was a function of the weights, and we define it as say 1 over p sum I going from 1 to p, some measure of error some measure of error, could be quadratic.
No.
Hmm?
No.
Who is taking notes? Okay. And so with in gradient descent, I hope, is this still okay? You never know where exactly the regular gradient descent. In each step, we changed our weights to our weights minus some learning, constant, the learning rate, times the gradient with respect to W of epsilon training, right? So this requires going over all the examples and calculating the gradient. This form of learning is sometimes called batch learning. Okay, this I don't know if I can write here, so we'll do it in another way. Batch learning. And it's sometimes inconvenient to do it this way, and certainly biologically it's not very plausible that the brain kind of iterates over a set of examples again and again. So now we turn to discuss first of all online learning. Actually, this should be part of the title here, online learning, because it goes together in what I will discuss. So we first of all think of a somewhat different framework for how the learning might work. We imagine that we have examples again, x mu and y mu, but now, and these examples as before are drawn from some distribution. But now we don't have a prescribed set of examples that is drawn once. We just keep drawing examples again and again from this distribution. We usually don't get back to an example. We might not get to an example more than once, but we just draw them from this distribution. And in each step, we perform some update on the weights. And so the update on the weights will have the general form that W on time step t plus 1 will be W in step times t plus some function. The function is some function of xt plus 1, yt plus 1, and wt. And we will discuss in a moment what this function is. So this is online learning. We do some few examples again and again. Note that in this formulation, we can't really talk in a very meaningful way anymore about the training error. We don't have a concrete set of examples that for which we want to consider the error, because we keep getting new examples. But our goal is might be to eventually have a low generalization error.
Do we have the same architecture as before with all the layers?
This is very general, so this can be, what I'm discussing for now can be done in any architecture. Okay, And we're not cycling through examples again. Okay, so now this is online learning, and stochastic. In stochastic gradient descent, the rule that's applied here is that Wt plus 1 is equal to Wt minus eta times the gradient with respect to W of the error only the error of our approximation in the last example. One thing that I should say, the way I'm describing it, I'm assuming that the y's are continuous variables, and so it's more meaningful to discuss the error over continuous variables, the gradient of the error. Okay, so this is what we're doing. Now, is this really what ideally you would want to do? No. Why not? Okay, so ideally we would want to ideally we would want to put here the generalization error, right? Now, the generalization error I can write as the average over this of this thing, x, y of x so let me write the average of this thing over the distribution P of x. That's what we would want to do.
Isn't it also true for the batch learning case?
Yes, that's true. But in the batch learning case, at least it's clear to me what we're doing. We're minimizing so right. In the batch learning case, instead of minimizing the generalization error, we minimize the training error. But at least the training error is an average over many examples. So at least in the limit where the number of examples goes to infinity, we're actually minimizing the generalization error. Right? Here, the situation is much worse. You can imagine that, suppose that we actually managed to find the correct, the weights that really minimize the generalization error. Then in general, whenever we present an example, this rule will shift us from these weights, because the particular weights that minimize the generalization error, the averaged over all examples, might not be the best weights for any given example, right? So this rule will actually push us away from this ideal value of the weight. So we want to understand why, whether and why, nevertheless, this rule is useful. So what can we say about it? Is there any relationship that we can write between these two rules? Is there any relationship that we can write between these two rules? Good. Okay, so on average, what we can say is that when we apply this rule, we're going in the right direction. On average here, Wt plus 1 minus Wt on average, averaged over P of x, will be minus eta, the minus eta, the gradient with respect to W of the generalization error. Let's write it precisely, the generalization error. Right? Right, where this is the generalization error. So on average, we are doing something useful. So what can we expect that will happen when we apply this rule? let's just conceptually imagine that our weights are in some n-dimensional space, okay? And these are the weights at time t. We see an example. We change the weights to some other weights, and on average we go in the direction of the optimal weights. Let's just imagine that the optimal weights are here. Oops. Are here. Now, maybe for the next example, maybe this rule will take us here, and but we kind of you could imagine that if we're very far away from the correct weights, maybe this rule will get us closer to them. But we'll even kind of at a steady state of this dynamics for the weights, we will hover around the best weights, but we will not be precisely at them. So what controls how precisely we will get to the optimal weights? Good, eta. Why can we say that? I mean, to have a good approximation of the optimal weights, do we want to make eta small or large? What? Small. Why? Right. So one way to think about it is that instead of going in these very large steps, we go in smaller step each time, and while we're doing it, we're actually averaging over more examples, right? So essentially, having a small eta, we'll show it more formally in a moment. Having a small eta is like averaging over more examples over the time in steps of these iterations, over a number of iterations over which W itself doesn't change too much. Okay, so if eta is extremely small, we can say that over a fairly large number of iterations in which W doesn't yet get a chance to change much, we're averaging over many examples, and therefore we're getting a good approximation for the gradient of the generalization error. Question?
Yeah, what do you mean we're averaging over?
Because we're doing many steps. We're doing many steps of this iteration. In each one of them, we're taking the example from the probability distribution of X, and we're kind of summing up the contribution from each one of them. So the direction in which we're going is now not coming from. Suppose that I make eta 10 times smaller. So over the typical number of iterations in which W changes significantly, I'm sampling now 10 times more examples. And since I make
averaging over this process.
Well, but in a sense we are averaging, because the smaller eta is, again, the over say, okay, you know what? I will do it more formally later on. Okay, so I think that it will become more clear. But this is just now trying to give the motivation. Yes.
Are we interested in the average of all the W's we have, or in the final W?
Okay, this is a good question. There is a whole dynamics for W, and
Like if we're just averaging, then eta wouldn't matter because we're just.
Right, but we want to get in a given instantiation of this learning, we want to to find good W's. So in that sense, I think it's intuitively clear from the discussion that if eta will be large, then we'll constantly kind of jump around close to the best W's, but we will be more far from them. And if eta is small, then we will make smaller steps. We will remain closer to the best weights all the time, right? What is the drawback of making eta small? Time. It will take more time to learn, right? So there's a trade-off here. Okay. So what are the kind of questions that we might want to ask?
When do you stop?
In principle, you never stop. But you could stop.
What would make you want to Unless, I mean, not only the case of you.
Well, in principle, you could monitor, the size of your errors and stop when the average error is sufficiently small or something like that. Yeah. So, so what are the kind of questions that we can ask? So, for one thing, right, kind of related to the question that you asked, we have here now a random process in terms of the W's. The W's have some random dynamics. What is the source of the randomness? The choice of the examples. So I should mention that when people say stochastic gradient descent, this is more general than what I'm discussing here. These are situations in which you kind of estimate the gradient of something. Here it's we want to estimate the gradient of the generalization error. And you have some stochasticity in the process, okay? So we don't know how to evaluate the gradient of the generalization error. So instead, we kind of evaluate some stochastic version of it, which is this. So there are other ways in which randomness can be introduced into learning algorithms. For example, it might be that we don't even know how to calculate this, the gradient for each example. And then we might want instead to kind of sample randomly, go in different directions randomly and use the change in the value of the function as a way to assess whether we're going in a good direction or not. I'm not going to discuss that kind of version of stochastic gradient descent, but I just want to mention that the term is more general than what I'm doing here. So here, the stochasticity in the dynamics of the weights comes from the choice of the examples. And therefore, the weights are some random process. They start from some initial choice that we have, but hopefully, after a long time, they will kind of reach the best weights, and then they will hover around them. And therefore, we can ask at steady state, after a long time that this algorithm has been running, what will be the distribution of W?
That you think that they're already good enough?
Right. Well, so for example, so yeah, there are different questions that you can ask. What is the mean of W? W when t going. Let me write just infinity here. So for example, on average, are we going to be close to the optimal weight? And then the next order thing to ask is, on average, how far are we going to be from this average? How much? If we go do this algorithm for a long time and look at all the weights in many steps, they will kind of form a cloud around the average. So what is the width of this cloud? So this is, asking something like what is W infinity square. I'll write it a bit sloppily. Because W itself is an n-dimensional vector, so we might want to say something about the covariance of this vector. Okay. Let me even say delta W. So delta W would be the difference with respect to the mean. Is it small? Right? We would want it maybe to be small. So this is one kind of question. What is the distribution of the weights after at steady state, after a long time that we run this algorithm? But then, as we discussed, we might care also about the speed of the convergence. So we discussed the fact that making eta small makes this small, so that's good. But making eta small makes the speed of convergence bad. For quick speed of convergence, we might want to make eta large. And another kind of question that we might want to ask is, what is the average generalization as a function of time? And why did I put the t here? So if we would ask, suppose that we run this algorithm again and again, and monitor at each step what is the generalization error, suppose that we be able to do it, then hopefully this function averaged over many instantiations of the learning will be some decreasing function and will reach some value which is close to the optimal generalization error. Right? Okay, so
Between time and number of examples presented?
when I say time right now, all I mean is number of examples. It's exactly the same thing.
And do I show the same example twice?
You might. In this formulation, as I mentioned, the examples are drawn from some distribution. Now, if the distribution is a continuous distribution, then the probability that you will choose exactly the same thing twice is 0. But if it's discrete, then maybe it could happen. So it depends on the context. Okay. All right. So what I want to do now is just to tell you some things about how about the behavior of this quantity. I will not prove it. So I think I will focus on this, but everything I will say is also related to these two, to the other two questions. So where should I do it? I'll do it here. Behavior for small eta. So part of it we will kind of see, but part of it I'm just telling you. So so under some conditions, I will not specify them exactly, and in this eta is sufficiently small that it's possible to show that the behavior for large T will be the following. So e.g., the generalization error of Wt when T goes to infinity will behave like the generalization error of the optimal weights, and I'm assuming here that there is some optimal choice of weights, some minimum of generalization error. But really, what typically happens is that this is some local minimum.
So, at what sense is the optimal weight?
Right. So it's not well. We discussed this also in the context of stochastic of a non-stochastic gradient descent. We're not. There's no guarantee that stochastic gradient descent will lead us to the optimal weights. If this depends on the structure of the problem, but so some problems, which are called convex problems, stochastic gradient descent which means that they don't have local minima. A gradient descent and stochastic gradient descent are guaranteed to reach the minimum, but other problems where there are many local minima of the generalization error, in general, what will happen depending on our initial conditions, and in this case also depending on the realization of the examples, will reach a local minimum. By the way, these days in deep learning networks, it's very clear that this is what is happening. But apparently, I'm not an expert on this. The claim is that the landscape actually has an extremely large number of local minima, but they're all one can prove instead of what you would naively think that you would want to prove, that there's just one global minima and you're going to get to it. That's not the case. There are many local minima in many problems, but there are ways to prove, at least for some problems, that all these local minima have similar errors, so that they are almost equivalent to each other. That's just an anecdote because we're not getting into these topics. But anyway, so the behavior for large T, what I actually, the precise way to think about it is instead of saying that we're averaging here only over many instantiations of the problem, let's just imagine that we started with some initial condition, and then we see many stochastic choices of the examples, and our algorithm kind of converges. Then it will converge to some particular local minimum. The particular local minimum that it will converge to might depend on both on the initial condition and the choice of the weight that we've seen, and then it will kind of the generalization error if we average over long times, over many examples, the generalization error, what we would see is that it behaves like this, plus some constant proportional to eta, which I will call A, plus some other constant times something that decreases with time. So you can see in this expression that the choice of eta affects two things. Maybe here I can still write.
What are A and B?
So A and B are some constants that depend on the problem, on the distribution of the examples, but they don't depend on if eta is small, they are no longer dependent on eta. So this encapsulates the dependence on eta. So you can see that eta affects through the term that involves A, the constant A. It kind of involves the width of the steady state distribution around the optimal weights, right? The reason that we're not really reaching the generalization error is that we're kind of hovering around the optimal weights, and that increases the generalization error beyond the minimum. So this A is larger than 0. And so eta affects the width of distribution around optimal weights. And through this, the average generalization error. And in this term, you see that eta affects the speed of the convergence. So there's a factor here, lambda, which depends on properties of the problem. And essentially, when t is large compared to lambda, this term goes to 0. So this lambda really tells us how many examples on average we need to see to converge. The larger eta, the faster we will converge. This term would exist even if we would be doing a regular gradient descent on the generalization error. So if you want to understand what this is, we can ask, suppose that we would do precise gradient descent on the generalization error, then there is some deterministic dynamics of the generalization error, and it will behave like this. The error as a function of time will behave like this. So this exists even for also in exactly the same way also for gradient descent on epsilon g. So B affects the eta affects the speed of convergence. Okay. What else do I want to tell you about this?
How do you get to this expression?
Oh, I'm not proving it, but one can prove this. We're not going to. I'm just telling you that that's the case. Okay? Yes.
You say that eta A is the term controlling the width, basically.
Yeah.
But this, as you wrote it, it's an equality expectation. So this is just a bias term, no? So how does it relate to the actual?
No, because The reason it's not a bias is that the generalization error has a minimum at W star. Now, the fact that eta is finite means that, as we saw in this picture, that we're kind of hovering around this value, and we might do it with zero bias. Okay? Still, even if we're doing it with zero bias, because the generalization error it has a minimum here, if we're around this point, we will get a higher generalization error. So all this is encapsulated in the value of A. Okay? Does this make sense? It's true that just writing this, you cannot tell whether A is coming just from the fact that we are on average. It could be that on average the weights are the generalization error, and all this term is coming from is from some variance around it. It could also come from bias, and in fact it comes from both, because there could be some bias which goes to zero as well when eta goes to zero. Okay. And there's an interesting theorem. So now all this suggests that, as we discussed, there is some trade-off here, that we might want to make eta large so that we converge quickly, but the disadvantage of that is that then at steady state we'll be far away from the best weights. So this actually suggests some that we might want to do something a little better than what I discussed so far. Any ideas? To change eta, right? It makes sense that maybe you want to make eta relatively large at the beginning, so that we quickly find the correct weights, and then gradually decrease it, so that kind of gradually decrease this cloud around the best weights in order to improve our approximation. And so there's an interesting theorem. Again, this is not something that I'm proving, and I'm not even careful enough in telling you what are all the mathematical requirements. But the theorem tells us that the following, that W will converge to a W star, which is the minimum over W of the generalization error. Could be a local minimum. If eta t, so now we imagine that the etas themselves, we decide on some protocol in which we're decreasing etas as t increases. So the idea is that eventually eta goes to zero, and because eta goes to zero eventually our generalization, this cloud shrinks to zero, and we get to zero generalization error. But in order for all this to work, we need to do this not too fast and not too slow. So the sum of eta t from t equals 1 to infinity should diverge, which means that eta is not shrinking to zero too quickly. Right? And on the other hand, the sum of the squares of the etas is finite. So this means that in order for this sum to be finite, eta should shrink sufficiently fast, so not too slow. And so, for example, you could choose, eta t could be some power law. A is not good, alpha. T over nu. And in order for both of these conditions to be met, then this nu must be larger than half and smaller than 1. And then these two conditions are met. So this kind of tells you what is a good way to decrease eta as a function of time in order to reach the goal that you're really shrinking the generalization error to 0. What? Yeah, in principle it could be anything, but it should be small enough, because all this theorem is correct if the etas are sufficiently small all the time. Okay, let's take a break now until 1. את משתמשת בו בזמן השיעור?
זה כאילו אומר, זה כזה, יש איזשהו שלב מבחינת האינסוף, שבו כל מה שאתה עושה זה
כבר להסביר, הוא לא אמור להיות יותר משמעותי.
באיזשהו משהו שצריך...
כן, כמובן התכוונתי ב-A וב-B, פשוט התכוונתי האיבר הזה והאיבר הזה.
זה בכמה גדול לאחר. אז זה
התכוונתי
מה כל הבעיה זה סביב בקונטקסט.
תפקיד הקונברז'ן נקבע על ידי הלמדה שלו.
זה נכון מה שאתה אומר, אבל זה לא אומר על הממוצע. בממוצע עדיין צריך לתת ליפול במקום הנכון. בגלל שאם כל מה שאתה עושה זה הקבוצות האלה.
לא, השאלה היא איך אתה מחשב. כאילו, השאלה איך אתה מתחיל את W. אם אתה רק לוקח את W האחרון, התשובה היא לא.
לא, אבל מה זה לוקח? אבל אני מסתכל פה על...
אם ה-W, כן, אם ה-W...
לא, זה לא משנה. זה לא משנה. לא, התוחלת כאן היא על הרבה אינסטנטים. סליחה, סבבה, לא, אני בטח, זה כיף. לא ראיתי זה אף פעם. לא, הוכחה אחרת. זה עם התנאים של ה-sum of squares, זה ממש מפורסם.
אני אומר כמו שמגבלה.
לא, אני מתכוון שלא ראיתי בכלל את הניסוח של הדבר הזה. כאילו, פשוט את הביטוי. כאילו... אני מבין אינטואיטיבית, אני פשוט לא מבין איך זה, כאילו... משהו לא שם. אני ממש שאלתי אותו, כאילו... איך יכול להיות, אם הדבר הזה הוא שוויון בר תוחלת, זה לא אמור להיות, אני לא, כאילו לא.
אתה מבין איך זה תוחלת?
לא, אני לא מבין למה יש את הטרם הזה של ה-A בגדול. כאילו, בממוצע זה אמור להיות, הממוצע אמור ליפול על במקום הנכון, הרוחב, כאילו, כי זה לא ממוצע שאמור לזוז, זה באמת אבל. אבל אני לא רואה איך A משפיע פה על הווריאנס, A זה...
זה משהו שנע סביב זה.
אבל זה נע סביב זה ובממוצע זה נופל על... זה נראה כמו בייסטר, זה לא ממש שולט בווריאנס.
מה הוא אמר לך? שלמה זה לא בייסטר?
לא הבנתי, אז אני לא יכול לחזור על זה. כאילו, הבנתי את המילים.
כן, זה מזל.
כן, הם 4,000 במקום, פשוט כאילו התחילו לעבוד עם העסקים ששיתפו פעולה יותר מהר. כאילו, היו שני מקרים שאי אפשר לעשות כלום, ושניים צריך כאילו לגרום לחוקים שלא עושים גם לעשות משהו, כאילו, סתם שם. ממש, הם ממש, הם פשוט נורא חכמים, הם באמת כאילו, ממש מוחות בחיים. הם נורא חכמים. עוד פעם, הם לא באמת עולם תוכן, זה לא שכאילו אתה
לא חשבתי כל כך רחוק. התחלתי לראות.
עכשיו, הבעיה שהוא אמר בסוף שכאילו המוח לא פתוח מספיק, חייבים לנקות אותו, כאילו, ולא משנה גם לרשום ממנו, כאילו לא סתם לא חייבים שתשמע כמו פתוח. כאילו, עכשיו הוועדות האתיות לא מאפשרות כלום. כאילו, בעיקרון, מה שגם אורי וגיא רוצה, שכאילו אי אפשר לומר שהוא לא אוהב את החוקים, הוא באמת אוהב אותם. שכאילו כל מי שלא יודע, כל מי שעובד מסתובב בפקטוריאל, יש משהו בדרך, הוא גבוה. ממש מדהים. הוא כזה, הוא נכנס לזה כאילו, הוא מכיר את כולם. קיצור, אז הוא כשיש לו קוד שלא ממש משתף פעולה, אז הוא פשוט עם לא פחד לעשות אותו עם הקולר, הוא מראה לו את הדרך. הם כותבים את זה מאוד מהר, ואז חצי מילדים טובים, אז הם לא מרשים לנו לעשות את זה, כי שזה מלחיץ, משהו מוכר, ואני לא יודעת. סבורי עובד כל הזמן פשוט לא שמים לב, כי הוא עובד עם מערכות קטנות ולא אגרסיביות, לא רואים מה שאנחנו רואים. אצלנו כל דבר שאנחנו לא עושים, מסתכלים במצלמות, אז על כל דבר הם אומרים לי מה תעשו אותו יש לו את זה. אז מה שאפשר לעשות זה שראש הוועדה הגיע לשבת איתנו כאילו במעבדה שגם מה לעשות, שגם אנחנו להעיד אין להם, זה בדיוק העניין שאין להם אין מה חוץ מזה ויצמן, אין כלום כאילו אין הרבה אנשים שמציגים את זה כאילו אין להם באמת, גם בבחינה הם לא באמת עושים בראש, עושים צלבים כאילו, זה לא אז כאילו יש את המאמן קודמים וגם אחר כך המאמן שאם באמת תצטרכי לעבור הדרכה לילה כאילו יאללה וזה, אבל כאילו היא עובדת עם דיני הנחיות, זה לא שופטים שעושים להם קוראים, זה לא איזה משהו מאוד אז היא לא כאילו מבינה את מה שאנחנו צריכים לעשות, וגם אין לה שום אינטרס שאנחנו נלך כאילו למה האימון שלה קצת מוזר כאילו
Okay, so what I want to do now is just I'm not going to prove this, but I want us to understand more carefully why it is that when eta goes to 0, we're actually reaching the generalization error, the optimal generalization error, or minimizing the generalization error. And what I want to argue is that when eta approaches 0, we're essentially implementing gradient descent and not on the generalization error and not stochastic gradient descent. So this is related to some questions that some of you asked. When I said this, it wasn't sufficiently clear, and hope that this will make things more clear. So let's do this here. So what I want to do is to contrast two different versions of the gradient descent algorithm.
What is what is the word there? Or?
On. Okay, on EG. Let me just write down here the rule that we're applying in each step: WIT plus 1 minus WI. Okay, I'm using slightly different notation here. I'm putting the iteration in a subscript, and I is like we have a set of weights, so a set of parameters. This could be the weights in a neural network, and these are the indexes now in the lower indices. So
Not a vector now?
it is, but I'm writing explicitly the change in the ith element of the vector, and I'm putting the t as a superscript. So the rule, right? The rule is that we take the derivative. The rule for that we apply in stochastic gradient descent, that we take the derivative with respect to wi minus eta times the derivative with respect to wi of the example for w, where w is equal to wt. That's the rule. And now what I want to do is to contrast two versions of doing this. One is where we just do this. And so let's call the eta that we use eta 0. And the other one is that we will make eta 0 smaller by a factor m. So but in order to compare the two, I'm going to consider at once m steps of this one. So I want to compare what can I say about the change in the weights in one step here, or the change in the weights in m steps here. Right? Because we're changing m, we're making the change m times smaller, we kind of expect that on average the change will be the same in these two cases, but that's just the average. All right, so so let's write down exactly what happens here. So what can I say about W after m steps versus of this algorithm, in this case, where eta is eta 0 over m? what can I say about this change? So it's given by m applications of this rule. So it's going to be minus eta 0 over m, and now sum over I going from, or a going from 1 to m, epsilon of x t plus a, yt plus a, and y and w. I will write this directly here, w t plus a minus 1. I should put this in a subscript, t plus a minus 1, because this is what I'm doing here. Okay, so this is precisely the change, right? So now, if I want to compare this somehow to what we're going to do here, yes? Yes, the derivative is missing. So sum over a going from 1 to m, d to d wi. This. Yeah. Now, if I want to compare this to one step here, one thing to note is that here we're evaluating the gradient at the position that we get to after each one of these m steps, whereas here we're evaluating the gradient once at the initial step. So I want to write something which is kind of similar to this and then write the corrections to that. So what I will say is that this is minus eta 0 over m sum over a going from 1 to m d to dwi of epsilon. Now I will put here epsilon xt plus a, yt plus a, minus is fine, and I will put here wt, and I need to correct. How can I express the correction to that, to this, to what I wrote, right? The difference between this and this is that here it's evaluated at wt plus a minus 1, and here it's just evaluated at wt. So what can we do? Do a Taylor expansion, yes. So why can we do a Taylor expansion? Because our assumption is going to be that eta is small, okay? Both eta 0 and certainly eta 0 over m are sufficiently small that we're allowed to do this. So if I do this, what I need to add now is kind of a sum over the sum of the derivatives with respect to every element of w of this function. So I will get something like minus eta 0 over m, sum over a going from 1 to m, and then I will have a sum over all indices of w, sum over j, d to dw j, and there's the original d to dwi, epsilon of xt plus a, yt plus a, wt, we're now evaluating things, wt, times wj t plus a minus 1 minus wjt, something like this. And there are even higher order terms. But the crucial thing to note is that this term shrinks to 0 as eta goes to 0. So this term itself is of order eta, at least of order eta, and therefore, or eta 0, and therefore all this term, all this expression has an eta here and something that shrinks to 0 when eta goes to eta 0, or eta 0 here and something here that also shrinks to 0 when eta 0 goes to 0. So all this thing is of order eta 0 squared. at least. No? It's not?
I don't see whether.
Because the changes, all the changes in the W in every step are proportional to eta, to eta 0.
What's in the WJ what?
Wj t, this is how much W changed between the step t after a steps versus, okay? So the changes in W that are induced by the learning are proportional to eta 0. And therefore there's something here which is this term shrinks to 0 linearly with eta 0 as eta 0 goes to 0.
And can you explain why you're using the general expansion here?
Because the explanation is in what I'm going to say next. I'm assuming that eta 0 is small, and because I see that this thing is proportional to eta 0, and I have another eta 0 here, then I argue that all this correction to this expression can be neglected if eta 0 is sufficiently small, because this is proportional to eta 0. This is simply proportional to eta 0. This is proportional to eta 0 squared. So when eta 0 becomes, if eta 0 is sufficiently small, I can ignore this term, and that's just the reason. The reason I'm doing it is that what I want is to work with this term, which is more similar to, because here we're evaluating W all the time at the same position. And so again, the argument is that if eta 0 is sufficiently small, it's justified to do this. Okay? Okay, now, yes.
Can you explain why the correction again?
Okay, because we're doing m steps. In each step, the weights are changing, right? So in each step, we're evaluating this function at a different value of the weights. We started from the initial, we either do one step that's with size eta 0, or we do m steps with eta 0 over m. And in the second case, in each step, the weights are changing. Okay, so this expression is evaluated at a different set of weights. Now, I want to compare the change in the weights after m steps to the change after one step with eta 0. And in this expression, for this case, I'm only evaluating the weights at their initial position, or to do just one step. So it's convenient to me to look at this expression where I replaced each one of these W's by WT. But the question is, this is not exactly the same. This is not the same as this. So I write explicitly what is the difference between this and this using a Taylor expansion. The Taylor expansion has additional terms, even of higher order. But now I claim that if eta 0 is sufficiently small, then this term is negligible compared to this one.
Yeah, my question was, why is this a difference between them?
Why is there a difference between what? Between this and this?
No, why is this a difference between
Because what I did is a Taylor expansion. So I'm evaluating this function at this value of W, and I can approximate it as the value of this function at a different value, value of W, plus derivatives with respect to each element of W times the change in W. So this is just the first term in a Taylor expansion of this expression as a function of the weights. All right, so now once we established that we can, for small eta, we can neglect this term, we can reach some nice conclusions. So it's eta 0. I'm just calling it eta 0. Okay, there's eta 0. I want to compare choosing eta equals eta 0 versus choosing eta equals eta 0 over m and doing m steps. So here it's eta 0. The learning rate is eta 0 over m. Anyway, what we so far we did is that we justified why I can say that WIT plus A minus WIT is approximately given by minus eta 0 over m d to dwi, sum over a going from 1 to m, epsilon of xt plus a, yt plus a, wt. Now let's ask ourselves, what is the average change, therefore, in w after these m steps? So wit plus a minus wit, what is it? How can I write it compactly? It's average of what? I don't even want to write average. I want to already write something. Yeah. Each one of these terms, the average of it is the generalization error evaluated at wt. We sum up m of these terms, but we also divide by m. So the average change in w is minus eta 0 times the derivative with respect to wi of the generalization error evaluated at wt. And that is exactly the same, would be exactly the same also in this case. In this case, m is equal to 1, and you see this does not depend on m. The average change in the w's does not depend on m, and it's the gradient. Okay? But so what have we gained by looking at m steps? The variance will become smaller. So we want to see that the variance, or not strictly speaking, not the variance, that the variance will become smaller. So what I want to write down is the variance. Let's call this delta wi. So the variance of delta wi, what is it? So when we calculate the variance of something which has a prefactor in front of it, the prefactor comes in a square, right? So I have here eta 0 squared divided by m squared. And then note that I can think about each one of the terms here as an independent random variable, right? The randomness comes from the choice of the examples. Since we're evaluating all of them at the same place, this is what we gained from this approximation. This is like a set of identical variables, each having the same variance. And so in independent variables, when you calculate their variance, the variances just sum up. So I can write here that I will have here m times the variance of d to dwi epsilon of x, y, wt. Variance over what? Variance over realizations of the examples, right? P of x. But that's nice, because you see here that here we have one factor of m, here we have m to the power 2. So this is proportional to eta 0 squared divided by m. Which means that if we look at these combined m steps, and we make m smaller and smaller, we make m larger and larger, so that we make more and more small steps. On average, we're doing the same thing, regardless of the choice of m, but when m becomes large, the variance of this compound step, where we did these m smaller steps, the variance goes to 0. Variance goes to 0 means that essentially, in the limit of m going to infinity, there's no variance. So in the limit of m going to infinity, we're precisely going in the direction of the gradient. And intuitively, it's quite clear why that's happening. Over these m, we're averaging over many examples. So we're actually estimating the generalization error well. Okay. So so the conclusion, I I write it just again. The conclusion is that when m goes to infinity, and therefore eta goes to 0, we're implementing gradient descent on E as a generalization error. Okay. Any questions on this topic?
Maybe it's very basic, but how do you see from what you got about the expectancy and the variance that you're exactly
That I am what? I see here that on average I'm doing the generalization error, and variance goes to 0. If the variance goes to 0, I'm doing it precisely. Okay. So next thing that I want to do is to discuss another example of a kind of stochastic gradient descent, which is useful sometimes in general optimization problems in which we don't know how to evaluate these gradients. But also it's interesting in the biological context. And this is a learning algorithm which is called reinforce. It belongs to a larger class of algorithms. I'm doing a particular example. Relevant paper is from 92. I'll put it on the Moodle. And so, first of all, I want to define a somewhat more broad setup than what we discussed so far, and then discuss the learning algorithm. So the setup is a little bit, as I said, the setup is a little different from before, and we will imagine that we have a neural network, and the neural network has in it unit activities that I will call yi. Okay. And there are inputs to the network. And I will call them x0i. And I'm putting here the 0 to designate that these are the inputs, because I will use x also for activities within the network. You will see in a moment. So x0i's are the inputs, and they come from some distribution. Okay. And so what I'm going to do is that I'm actually going to lump all these together, both the inputs and the activities, into one vector that I will call x. Oops. And the reason I'm doing it is that we're going to think about a kind of feed-forward neural network, and the y's kind of in each layer will be the inputs to the next layer. So this is kind of similar to what we did when we discussed the backpropagation algorithm. So it's convenient to me to think about this whole thing as one vector. These are the inputs to the input layer. And one thing that I'm going to do now, which is different from what I did when we discussed the backpropagation algorithm, is that I will imagine that the units of the network themselves might be stochastic. So what this means is that instead of saying what is the output of a given neuron unit in the network given its inputs, I'm going to say what is the probability that it will generate a certain output given its inputs. So we have stochastic units. and they're defined by some probability functions, which are say what is the probability for unit I to output value y given x, and this will depend also on some parameters that you can think of as the weights, the synaptic weights. So yeah. So we will discuss this in a moment. Okay. In principle, in the way that I'm writing it now, it might not be well defined because the y can be depend on any other on any other y in the network, and therefore maybe these equations are kind of interrelated into each other in a way that does not define the y's completely. But we know some examples where it would be okay. For example, in the feed-forward networks that we discussed last week, everything is fine. Each one of the y's only is determined by the previous y's, right? So we'll generalize this a little bit. We could imagine any architecture. You know what? Maybe I'll get back to that point a little bit later because I want to first explain a bit more about what I wrote here, and then we will discuss this point. So, just as an example, we could imagine that we have a binary neurons. So the y can be either 0 or 1 or -1 or 1. Let's say 0 or 1 for now. Let's say it's -1 or 1. Okay. And then we would need to define what is the probability of yi to be equal to 1 given the inputs, given the weights. Of course, if we know what is the probability for the output to be 1, we also know what is the probability for it to be 0. That's 1 minus that. And for example, just as an example, we could imagine that the probability for the neuron to be in state 1 versus state -1 is some sigmoidal function of a linear combination of its inputs. So it could be some wij, j is some subset of the inputs, xj plus bi, and this sigma could be some kind of sigmoidal function.
What is the subset?
It's some subset of the, let's put here ji. It's a subset of the activities in the network. Okay. So we could imagine that each neuron has inputs from some of the other neurons, and maybe also from the direct inputs to the external inputs on the network. The neuron sums up the activities of the other neurons and maybe the external inputs with some weights, add some bias, and then this determines the probability of the neuron to spit out 1 or 0. Just as an example. Okay? I want to write down explicitly another example, which would be a Poisson neuron. So maybe we'll switch. So examples. Poisson neuron. So Poisson neuron can output not just -1 or 1, maybe it outputs an integer number or a non-negative number. And so we need to specify what is the probability for yi to be equal to n. We need to specify this for each one of for each value of n from 0 to infinity. And if it's a Poisson neuron, then this would be e to minus some rate, lambda I to the n divided by n factorial, where lambda I is some function of the inputs to the neuron. So this could be sum over wij xj plus bi, where j is equal to, it belongs to some subset. So in this example, the neuron spits out a number, say the number of spikes that the neuron generated. This is stochastic, but it's a Poisson variable with a rate that depends on the inputs to the neuron. Okay, it's just another example. Okay, but as we discussed and as you pointed out correctly, if I just write something like this, this might not be a set of equations which defines clearly what are the outputs of all the neurons. So what we're also going to assume is that this connectivity, which is defined by which inputs get into each one of the neurons, does not have any loops in it. Okay, so each neuron has its inputs, subset, and the inputs. This defines a graph, and the graph has no loops. So, for example, I am going to allow something like this. Okay, this is fine. There are no loops, and this neuron is the activity of this neuron is determined by this input. This neuron is dependent on this one and this one. All is completely well defined. But if I had loops in the so this is okay. But if I had something like this, I'm not going to allow it. This leads to problems in interpreting what these equations mean, because this depends on this depends on this, but now this depends on this, which depended on this. So we might get some set of equations that might not even have a solution. So I'm not going to consider such cases. Also, the fact that there are no loops is going to be important for the discussion of the learning algorithm that we will introduce in a moment. Okay? So feed-forward networks fall into this category, where you have clear division into layers, but it's a bit more general. Okay. Okay, and the final element in our discussion is going to be that there is some reward. So whenever our network is presented with an example and generates an output, there is a reward, and the reward is drawn from is also stochastic. So the reward is a function of x and y. And very generally, I will assume that it's a function of all the y's, but you could, as a particular case, you can imagine that there is one output unit of the network which determines the reward.
So the reward is not related to what the network did.
Exactly. So this is a very good comment, that you see that what I wrote here is that the reward doesn't care at all what are the weights. Okay? This does not depend on the weights. The reward depends only on what the network was presented with and what it did. Okay? And our goal, the goal that we want to discuss, is what do we need to do to maximize the average reward. So I want to maximize the reward. The average reward depends on the weights, not explicitly here. Right? This function does not depend on the weights, but the relationship between y and x does depend on the weights, and therefore it's conditioned on the weight. I'm writing that it's conditioned on the weights, and I will call this thing, this is a function of the weights. And what am I averaging here? I'm averaging here over the choice of the examples, the choices of the outputs of the network given the examples and w, and the fact that the reward itself is dependent on maybe stochastically on the inputs and the outputs.
What are the probabilities that you look at? I mean, what does it relate to?
Maybe I'll write this a little bit differently. The probability of R given X and Y. What was the question?
I just missed the connection between these probabilities. What the
So-
maximization?
So I'm saying I want to maximize the average reward. Now in this formulation there are many things that are random. I'm averaging over all of them. The weights are kept fixed, but given the weights, the examples are chosen randomly. The output of the network might be, doesn't have to be, but it might be, in the examples that we've shown here, it is a random variable conditioned on the inputs and the weights, and the reward might be a random variable conditioned on the input and the output. I want to average over all these things. Okay? Now, yes.
Maybe it's technical, but you write, do you mean that the reward is a vector in some sense?
Oh, sorry. Thank you. No, it was just my confusion. Yes, scalar.
So we don't care about minimizing any error here?
Okay, so this is a very general formulation of a problem which might have nothing to do with function approximation. In the past few weeks, we discussed the approximations of functions. But as a particular case, we can consider the case where our goal is to approximate a function. How could we map that into that problem?
The reward could be the loss or minus.
Yeah, exactly. So the reward could be the loss function that we use. The reward could be, say, the square difference between y and the desired output for f of x, right? The reward could be minus, as you say, because we want to maximize it. So it could be minus the square difference between f of x and y, where y would be one unit, the unit at the end of the, say, of a feed-forward network. Okay, so then that would be mapping what we discussed. We could take, say, the feed-forward network that we discussed previously, and take the output unit, and the reward would be the activity of the output unit minus f of x. All right. So now I'm going to tell you about a learning algorithm, which turns out to be a learning algorithm that achieves this goal, that it achieves this maximization of the reward. So the idea is that we present inputs. We present the inputs to the network. We observe what is the output. So iterate. Maybe I will write it like this. Iterate the following. We present an input. We observe the output and the reward. And then we make a change in every one of the weights in the network. So for example, in this network, the weights will be the connection between this and this, between this and this, and this and this, some parameters. But it actually can be more general than linear. We're going to do it with, we're typically going to think about the weights as some coefficients of linear sums of inputs, but it could be more general. This could be some function of the inputs which depend on some parameters, wij. So this is what I mean by the weights. And the change in each one of these parameters, or the weights, is going to be some eta times the reward times EIJ, and I need to tell you what is EIJ, okay? So eta is the learning rate. And EIJ is set up in a very particular manner to be the following quantity. It's a partial derivative of log pi of yi x and all the weights with respect to wij. Okay, so we provided the network with some example. It generated some outputs. And this is some kind of measure of whether it's more likely that this particular output that we got, would it be more likely to get that input or less likely to get that input if we slightly change wij. But we're doing it for a reason that you will see later. We're particularly looking at this function, the derivative of the log probability with respect to wij. Okay, so why is this interesting? So for one thing, you can ask. Let's think a little bit about EIJ itself.
To get output.
Yeah. So the network generates some output. The network generates some. Now, by output, I mean all the activities in the network, right? Because this is right, and for each one of them, we're now modifying some parameter that affects yi. This wij is some parameter that affects how yi is related to the inputs to the unit I. And the rule of the change is whatever it is. It's what is written here. But you can see that it's positive if the probability to get that particular value of y would increase if wij would be increased, and it would decrease if wij decreased. And this thing would be negative if the probability to get that yi decreases when we increase wij. Anyway, one thing that you can ask yourself is what is the average of EIJ? And it turns out, we will prove it, not today, we will prove that this is 0. So this quantity EIJ